Okay, good afternoon, everyone. Welcome to the fourth day and final day of our event and to our subsurface session. Don't forget, we have three rooms running in parallel, all with very interesting presentations, and you are free to move between them. At the end of each presentation, there will be a Q&A session, and you can make all the questions you want, even during the presentation. As a moderator to our session, we will have Christian Ninho. Christian is a geologist that holds a master from the Federal University of Rio de Janeiro. He worked at Ecopetrol, the Colombian Petroleum Institute, and Hydrocarbon National Agency in Colombia for 7 years. Then he joined Hess as a petroleum system analyst and worked at their London, Houston, and Kuala Lumpur offices. Since 2014, Christian has been working in Galp, here on Lisbon office, as a head of the business of Basin and Petroleum System Analysis Group. So please join me welcome Christian with a virtual round of applause. And Christian, the floor is yours.
Thank you, Bruno. Thank you for the introduction. I have the pleasure to introduce Professor Benjamin Kneller. He's a emeritus professor at the University of Aberdeen and currently a visiting professor for the Chengdu University of Technology in China. Ben was a professor for the School of Geosciences of Aberdeen from 2004 to 2018. Prior to that, he was at the University of California, at Santa Barbara, and also at the University of Leeds in the UK. His work has focused on the water systems and processes, often in collaboration with the oil and gas industry. He has more than 100 papers in academic journals and books, and he now undertakes training for the industry and works extensively with universities in China. So, Ben, please go ahead, and the floor is yours.
Okay, well, thank you very much, Richard, and thank you very much for the invitation to speak at this meeting. I'm a geologist, and some of the things I'm going to talk about may be somewhat new to some of you, but I hope even if you don't find them relevant, you'll find them interesting, but I hope you'll also find them relevant. I'm going to talk about deep water sedimentation, and in particular, I'm going to talk about contourites, which certainly will be new to some of you, and try and explain why they might be interesting.
Ben, could you share the screen? Sorry, we are not seeing the screen yet.
Oh. Should be shared. Yeah. Okay, can you see now?
It's coming. Yes.
Okay. Well, you didn't miss anything, so that's fine. Okay, so as I said, I'm going to be talking largely about contourites, which are mostly muddy or silty, but some have enough sand in them to form potential reservoirs. So they're increasingly being looked at as exploration targets, having been virtually ignored in the industry for forever, basically. And this is despite the fact that they're extremely common on modern passive margins, and they're often hundreds or even thousands of meters thick, so there are enormous volumes of these sediments which are being deposited and moved around by bottom currents. So we have to ask ourselves, why do we see so many in the modern systems and we recognize so few in the ancient record? I'm careful to say recognize rather than see them there. And lastly, I'm going to talk about how turbidite systems and mass transport interact with contourite systems, because much of what we might be looking for in the ancient record will be hybrid systems that have a component of both downslope and along slope processes. Okay, so this is the outline. First of all, I'll give you a bit more of a rationale behind the talk. Then I'm going to spend some time talking about the oceanographic processes which are responsible for creating these currents in the first place. And hopefully that will be of interest, if not entirely relevant to your exploration efforts. Then I'm going to talk about recognition, how we recognize contourites in the ancient record, whether we can recognize them. Then talk about these hybrid systems, and then finally wrap up with one slide at the end. So, as I've already mentioned, there are very few contourites recognized in the ancient record. Well, why should we care that there aren't any? And that's because we rely so much on analogues, outcrop analogues, to understand the subsurface. And if we want to understand the potential for contourite systems to create reservoir, we really need some analogues that we can go and get our hands on, so that we can understand the processes, we can understand the geometries, the architectures, and use those to populate any reservoir models that we might create for our contourites. When I use the word contourite here, I'm using it more or less synonymously with bottom current deposits. And although not all bottom current deposits are produced by contour current sensu stricto, the majority are, and that's because of the Coriolis effect that's due to the rotation of the Earth. Okay, so what controls these currents? I think the first thing that we have to be aware of is that the ocean is layered. It's not like that glass of Bailey's on the left with the ice floating on the top, which is more or less homogeneous from the top to the bottom. It's more like that layered cocktail on the right, where we have layers of water with different properties. And on that layering in the ocean, you can produce various phenomena, such as internal tides. Internal tides are like surface tides. They're driven by the sun and the moon's gravitational attraction, but they have much, much larger amplitudes than surface tides. They can be tens, even hundreds of meters in amplitude. And we can also produce internal waves, which are just like the surface waves, but again, they're much larger in amplitude. And these are capable of moving sediment around, particularly where we get these internal waves colliding with the continental margins and breaking, like surface waves, and stirring up sediments. And the bottom right-hand side of that image you see on the screen now, you can see a series of large sandy bed forms, more than 5 meters high, in depths of several hundred meters. So this is way below the effect of surface waves. Now, we not only have this layering on which we can produce waves and tides, but the layers are complicated, and the water masses that create them can be moving around in different directions, moving past one another. And the boundaries between those water masses can be unstable. So you see on the right-hand side, looking down from a satellite image, looking at the polar front, where there's a current in the bottom, which is warmer, moving in one direction, and the polar cold water moving in the opposite direction, and it's producing these big eddies, which are mixing them up. And on the bottom, you can see a vertical section, and that shows you that the layering is not that regular in the ocean, because the layers moving past one another produce large-scale eddies at their boundaries. On the left, we can see a representation of the complexity of the water masses in the South Atlantic, and you can see these water masses moving past each other. So what moves these water masses? Well, a lot of it's moved around by the wind. In the top left, you see the global wind circulation, called the Hadley cells. Those winds drive the surface waters in the large ocean gyres, which you see in the image on the bottom left. But those surface water movement can actually extend a long way down into the ocean, down to hundreds of meters. And we also get influences on a more local or regional level, such as tropical storms. And in the upper right, you see a typhoon, which is approaching Taiwan, which is at the upper left of the image. And on the lower right, you can see the effect that this is having on the water in the South China Sea. There's actually a track of a typhoon in the green dots, and you can see the ocean currents as vectors around the star, which it represents the position at the moment that those vectors were created. Now, water masses can also be moved around by density differences. On the left-hand side, you can see fresh water moving out of the Amazon. Of course, that's floating on the surface and moving past the underlying more saline water. And you can have water masses produced by salinity differences, where the salinity is higher rather than lower because of evaporation. In the bottom right, you can see a cartoon of the Mediterranean Sea, where evaporation is creating more saline and therefore denser water, and that's flowing over the Straits of Gibraltar as an underflow because it's denser. Upper right, you can see an example of the colder water, therefore denser, moving through the Denmark Strait and then cascading down into the bottom of the North Atlantic Ocean to the south. So temperature differences and salinity differences create different water masses which can move as a result of their density differences. And when we see the effects of salinity and temperature together, we produce what's called the thermohaline circulation, which is one of the most important contributors to the circulation of water in the deep ocean. If you look at the cartoon on the bottom right, it shows the seawater with some ice floating on the top in the polar regions. The water is cooled by the wind blowing over the surface, which is called evaporative cooling. It's a bit like going out on a windy day in a wet shirt. You get pretty cold. But also the ice, as it freezes, it extracts pure water from the ocean, and therefore the residual water becomes saltier. So we've got water which is cold and salty, and therefore it's dense, and it moves down over the sea floor into the deepest parts of the ocean. And because oxygen is more soluble in cold water than it is in warm, it carries oxygen with it into the deepest parts of the ocean, all the way down to the bottom of the Marianas Trench at the moment. It's 12 kilometers deep, and there is plenty of biological activity on the seafloor. So we have these various processes interacting, and these processes then interact with the topography on the seafloor to produce very complex patterns of currents. And I'm not even going to begin to go into the structures and architectures of the deposits that are produced as a result. That would be a whole series of other talks. So, coming on to why we don't see examples of these things in the ancient record. Well, is it because they're not there? And if they're not there, then why not? Or is it just because we don't recognize them and they are there? And if we don't recognize them, why don't we recognize them? And one possible reason might be that we're using the wrong criteria. Well, not being able to see Contourites in the ancient record could possibly be because the majority of Contourites today are on passive margins, and passive margin successions generally don't crop out on land unless they're uplifted, having gone through continental collision. And of course, continental collision doesn't really do sedimentary successions a whole lot of good. They get deformed and metamorphosed, and this could render them unrecognizable. Well, is that necessarily the case? Well, actually not. There's a couple of examples I'm showing here from foreland basins, which, although they're somewhat deformed, you can still recognize the sediments quite easily. On the left, we have part of a Triassic foreland basin from central western China, and even though the strata are now vertical, if you look in detail at them, you can see quite clearly the sedimentary structures. And I'm going to suggest that these two images in the center left are both Contourites, slightly siltier to finer grained ones on the upper image and much sandier ones in the lower image. And on the right, we have a not very good picture of a part of a 3.5 kilometer thick Silurian foreland basin fill from the UK, which in detail looks rather like the Chinese image on the upper left. It's mostly fine-grained. So, coming on to the next point, are we using the wrong criteria to identify Contourites in the ancient record? Well, if we look at the center left of the screen, you can see what have been considered to be a sort of standard model for Contourites. And on the right, we have the model for coarser grained ones. On the left, we have the finer grained ones. And you can see both of these models have extensive bioturbation. Now, these models are based on modern Contourites, or Contourites from the Cainozoic, on modern passive margins, which are, in general, heavily bioturbated. Now, if we look at that image at the lower left, the one we looked at in the previous slide, you may be able to see that there is no recognizable bioturbation in it. And so many examples that may be Contourites have been ruled out because they're not bioturbated. So why might they not be bioturbated? Well, if we don't have a thermohaline circulation, then we're not introducing oxygen into the deep ocean. And if you look at the image on the right, you can see the history of Phanerozoic temperatures, with the black line being the global average temperature and the purples on the top representing periods when the poles have been glaciated. And you can see that during a lot of the Mesozoic and into the early Cainozoic, the Earth has been ice-free. So we might expect under those circumstances that there would be very limited thermohaline circulation, if any, and therefore limited introduction of oxygen into the deep ocean. So we might expect our deep water sediments not to be bioturbated, or at least not extensively so. So we may be using the wrong model to identify our Contourites. What about the coarser-grained Contourites? Well, the sort of standard model for coarse-grained Contourites suggests that they're often cross-bedded. So we have to ask ourselves, are cross-bedded sands necessarily Contourite? In the center, upper center, we have an image from a relatively recent Contourite. This is taken from a core offshore. On the upper right, we have something that's been identified by some authors as Contourite, but in fact, I can be pretty confident this is turbidite for reasons that we can go into later. There's plenty of evidence that it is. And the lower right, we see something which it's very difficult to identify as either Contourite or turbidite. It might be one or the other. So some of these things are just indeterminate. So we come on to the notion of hybrid systems, which is where Contourites and sediment gravity flows are interacting. Sediment gravity flows being mass transport, that's to say submarine landslides, and turbidity currents. And we can broadly look at three different types of system. Those where these processes are contemporaneous, where you've got a constant background of contour currents, and then the episodic sediment gravity flows on timescales of weeks to thousands of years, depending on the system you're looking at. Or we may have alternating systems where periods with contour currents alternate with periods which are dominated by sediment gravity flows on much longer timescales of tens of millennia or longer. And then there are systems where we just can't tell. They could be one or the other. So let's have a look at a couple of examples of some contemporaneous systems. It's long been recognized that there's a possibility of contemporaneous systems, which is shown in this cartoon in the lower center, drawn some time ago by Shanmugam. It shows the turbidity currents moving down a levied channel, and the very low concentration upper part of the turbidity current is being moved to one side by bottom currents. Let's take a historical example, which is the Grand Banks turbidite, which was generated by a large earthquake on the Grand Banks of Newfoundland, offshore Canada, in November 1929. And this earthquake created a number of large slumps on the upper slope, as you can see in the image on the left. And it's estimated that about 60 cubic kilometers of mud failed on the upper slope. And in green, in that map, we have the deposit of that current. And it has about 120 cubic kilometers of sand in it, which was picked up en route down the slope channels and canyons on its way down to the abyssal plain. So we know there's 120 cubic kilometers of sand in the turbidite, and we know that about 60 cubic kilometers of mud failed on the upper slope. But we know that the final volume of the turbidite is only about 140 cubic kilometers. So there's a lot of mud missing, and independent estimates come up with about 20 cubic kilometers, but it may be as much as 40. So where has all that mud gone? Well, if we look at the image on the right, the vector arrows we show there are what's known as the western boundary undercurrent, and that's the thermohaline circulation, which has been pressed against the western boundary of the Atlantic Ocean by the rotation of the Earth, and that's ongoing the whole time. And probably after this turbidity current had more or less run out of steam, there was a lot of mud left in suspension, and that mud was moved out of the way by the western boundary undercurrent and is smeared down the eastern North American seaboard. Here's another example of potential hybrid systems. Now, this is taken from ancient examples. On the left-hand side, you see an image taken from mapping that my group has done in southern Chile of a large channel system. And on either side of this channel system, we have levees. Now, when turbidity currents come down a channel, you expect any overspill to be diverging away from the channel. And we know that this is a levee because we can see the thinning of the turbidites away from the channel and an increase in the mud content. But the currents that we measure in these turbidites are going towards the channel. And it's similar in the example from the right, which is from Mexico. You can see the channel belt with the currents going down from upper right to lower left. And in the white arrows, you see the paleocurrent direction that's expected from the overspill from the channel. And with the green arrow, you can see the actual observed examples. And those observed paleocurrents are actually parallel to the slope. The channel is coming obliquely down the slope, and the paleocurrents in the levees are going parallel to the slope. So it looks like what's happening here is that we have an ongoing background of contour currents which are subtly reworking the turbidites in the levees and just producing ripple cross lamination on the tops of each turbidite, which is what we measure to establish the paleocurrents. Now here's an example of an alternating system. This is from the Gulf of Mexico, just down dip of the Sigsbee Escarpment, which you can see in the top right image there. And top left, and the lower left image, you can see a whole series of furrows that have been created by contour currents during high stands. And in the upper right image, you can see the furrows that are present on the seafloor today in response to that's contour current. Now, these are alternating with submarine landslide deposits, and you can see an extract from a 3D seismic survey in the lower right. That image is actually showing the scoured surface beneath the submarine landslide deposit. So what's happening here is that the submarine landslides are occurring during the low stands, and the contour currents are dominant during the high stands. Here's another nice example of alternating system. What's happening here is during the high stands, we're getting contourite waves produced. And in the left-hand image, you can see at the upper half of the seismic section, you can see contourite waves. And on the seafloor, you can see these submarine canyons. If you look at the right-hand image, you can see the waves. The high amplitudes represent the turbidites between those waves. So the turbidites are coming down the troughs between the waves, and you can see at the ends of those troughs little slope fans, which is where the turbidites are accumulating. And again, what's happening here is that the contourite waves are being produced during the high stands, and the turbidites are coming down during the low stands. And here's an example from offshore Brazil. And here we don't know what the relative timing is. Upper part of the image, you have a fan which is sitting on a terrace. Some of those sands in the fan have spilt over from that terrace down the fault scarp into the terrace below, and then they've been reworked longitudinally by contour currents. Might be contemporaneous, might be alternating. Okay, so just to wrap up, currents affecting the modern deep sea floor are varied and complex, and incidentally, the facies are incredibly varied too, but we don't recognize many ancient contourites, and that may be because we're just using the wrong criteria. And differentiating contourite from turbidite is not necessarily straightforward, but perhaps it's not that important, since interaction between the two systems is probably the rule rather than the exception, and we should expect to be looking for these hybrid systems. So, thank you very much for your attention. Any questions?
Hi, Ben. Yes, there is a question. We have a couple of questions, but I think we have time for one. Question is, how stable through geological time are the currents? Should we look in areas of modern currents to find the paleocontourite deposits below? Offshore Mozambique seems to work.
Well, it probably depends on the time resolution you have. In the longer term, what's happening during today's relative high stand may well be reasonably representative of the way that contourite systems have developed in the past, but they may not have been consistent through the past. So, as I say, they might be alternating with sediment gravity flow systems. So perhaps through the Cainozoic, you could use modern systems as an analog for more ancient systems, but that's not necessarily telling you what's happening during the low stands. Okay. Incidentally, if you want to send me any of the other questions by email, I'd be glad to have a go at answering them.
Okay, absolutely. I do have one question, Ben. What are the main fields you remember, oil fields that have this type of deposits, and where?
Well, so far as I know, there are no producing fields, but that's largely because exploration for them is in pretty early stages, and it's only very recently that people have started recognizing them onshore as well. Really, recognizing that there may be enough sand in these systems is really a pretty recent discovery.
Okay, excellent. Here I have Joseph Plonkin saying hi. Okay, thank you very much, Ben. I think we have. I will send you another question that is here, but I will send you by email. I think we are done.
Okay.
Really glad for your presentation. Thank you very much. I think.
Thank you very much. I hope people found it of some interest.
Okay, absolutely.
Okay. Ciao.
Now we have Karyna.
Okay, I should disconnect at this point, right?
Okay, I think so, yes. Thank you, Ben. Hi, Karyna.
Hi, can you hear me?
Yes, I can hear you.
Good.
Nice to see you.
Same here. How are you?
Yes, I have the pleasure now to introduce Karyna Rodriguez. She has been visiting us in the last years, and Karyna is currently a VP for Global New Ventures at Searcher, and is a petroleum geoscience with more than 30 years of experience in different disciplines, mostly geophysics. She has worked for different companies like Pemex, BG. So her experience goes from seismic interpretation and amplitude anomalies, sequence stratigraphy, play analysis, going through prospect generations and volumetrics. And recently, in the last years, Karyna has been part of a group trying to optimize portfolios, no, Karyna? Exploration portfolios and working with top management to try to clean these portfolios and help us to look for oil and gas in mature and frontier basins around the globe. Okay, Karyna, so you have the, please go ahead with your presentation. Thank you.
Okay, thank you. I will share my screen. And
Perfect.
are you seeing my presentation in presentation mode, or are you seeing?
Well, presentation mode is fine, I think. Yeah.
Are you seeing it all right, or are you seeing my notes and you're seeing the next slide?
I'm seeing it fine. Bruno, can you help me? I think this is better.
Yeah, it's working now. Yes, it was outside, but it's working now. Yes.
Okay, it's working now. Perfect. Okay. Yes. Well, thank you very much for inviting me and for considering me. I am very excited in my new position at Searcher to be presenting this work on the Malvinas Basin because it's an area that I had been working on previously. And first of all, I'd like to thank the main author for a lot of this work, that was Krista Davis with Searcher as well, and she has done a lot of the work that I will be presenting. And then some of you may know my co-author, Neil Hodgson, as well. So we're going to start off by just doing a little bit of going back in time and looking at the stratigraphy of the Malvinas Basin. The Malvinas Basin is located in the southern tip of Argentina, just around Tierra del Fuego. You can see the location right here as I'm pointing to this. And we are going back to around middle to upper Jurassic times when this was just starting to open. So it was still a closed seaway. And what I will be doing today is I will be talking about two key source rocks, because it's all about the source rock. If you know where the source rock is, if you can actually identify a viable, good quality source rock, which has a widespread distribution, then you're halfway there into your exploration. So the main thing with the Malvinas Basin, and I'll walk you through where we are in terms of exploration, but it's very, very important to get the source rock and to understand the source rock and de-risk that. So when we go back to the Sinrus stages, there was the Chonaike large igneous province, which was in the area, and therefore you can see here in the stratigraphy that there are a lot of tops. We also have sandstones and we have volcanics, and these are all interbedded, but there are also inferred lacustrine sediments where we expect the organic rich sediments to be deposited, and those would be our potential source rocks during this time. And then you'll see over here where the Malvinas is located, and as I move into our higher stratigraphic levels, and we are moving from the Sin Rift into the main sag phase or passive margin phase. When we do that, you can see that at the base of that, just beginning of the sag phase, there's a spring hill formation. This spring hill formation is a very important reservoir in the area. It's where most of the accumulations have been found. It's diachronous, and you can see how it sort of backsteps from south to north. Then we have a series of the marine transgressions. So this is interbedded with marine clay stones. But in the Aptian, there's a major event. This is a maximum flooding surface, and we also know about the oceanic anoxic event. This is a global event. So this very rich organic layer is deposited here. This is the lower Inoceramus formation, which is one of the key source rocks as well. So we have two potential source rocks that we are going to be analyzing in a bit more detail and trying to understand where the source rocks could be located, might be generating hydrocarbons, and where are the structures that could be trapping these hydrocarbons. And then as we move up into the tertiary, this is more of the foreland stage. You can see that we're in the foredeep stage, and it's a combination of passive and active marine deposition, sandstones, shales, and carbonates. So we do have, again, some possible source rocks, but they wouldn't be very deep enough to be considered important. But we also have quite a few reservoirs which could become important later on. So what data set do we have available, or did we also have available back in 2017 through 2020 in order to carry out this study and de-risk the source rock in the area? There is a very, very large data set that you can see here. If we start off with the orange data set, that's important because it's been broadband reprocessed from field tapes, so pre-stack time migrated. And I will show you some of the uplift that we obtained. And I'm going to show you the uplift because it's so important. It just changes your view of the prospectivity in that area. And then the black lines are 156,000 kilometers of 2D, which have been post-stack reprocessed, so they have been merged into one contiguous data set by phase, amplitude, and time matching the data sets together with the 3Ds that you can see outlined here, 12,000 kilometers of those square kilometers of those 3Ds, so some down here in the main area of interest. And then you can also see all the wells which have been conditioned and have been rectified, so that we actually produced at the time a basin analysis report. And this is an example of the output of the conditioned wells. And this is all part of a database that was used to try to understand the prospectivity in this basin. So this is from the 2017 analysis. You can see that there are quite a few wells that have been drilled in the Malvinas Basin. However, this is still very much considered a largely underexplored, unexplored basin. And as usual, we usually go for the high structures, and then we haven't gone into the other types of plays that I will show you some of those that have not really been tapped into. But you'll see here, for example, the calamar that produced 3,200 barrels of oil per day with 37-degree API. Then the Salmon 1 and Salmon 2 actually flowed oil and gas and condensate to surface. So these are considered oil and gas discoveries. And down here we have oil and gas shows. Though the Cyclone 1 actually produced, it was quite a low production rate, but it produced from what was called basement, which could be actually the Tabifera formation, this tufaceous formation that is associated with that large igneous province in the middle to upper Jurassic times. And you can see here from the risk analysis that we carried out, this it shows in the shape of a wagon wheel, and the charge portion of this analysis is here in the right-hand bottom corner of the circle. And when it's red, it's high risk, and when it's orange, it's medium risk. And you can see that the risk sort of for charge increases around this area. And then I'll also talk about some of the blocks that were not awarded in that first round and what we actually know and understand about those blocks now. So first, as I said, I'm going to focus in on this broadband reprocessed data because it really does provide us with the insights that we need to understand the petroleum system in this area. As I said, the Synrift is a potential source rock, and so we need to understand and we need to be able to view and image this Synrift section. So first I'm going to show you an example of a reprocessed data set. We reprocessed this data in two phases only because of data availability. So as the data became available, it was reprocessed. It was then joined up and merged. So first I'm going to look at the 2018 reprocessing, and this is a legacy seismic section. So this is what we received. You can do some interpretation on this. You can see that there are some serious multiples in here which are really affecting the reflectivity
Karyna,
and imaging.
Sorry, we got out of presentation mode. Could you try? I mean, we are seeing the notes on the next slide.
Oh, okay. What if I do that?
That's better. Much better. Thank you.
Are you back? Okay.
Yes. Thank you.
Okay, thank you. Yeah, so here what we can see is that the reflectivity is not great. I mean, we can do some interpretation, but the continuity and the amplitude content isn't great. But really where we run into a lot of issues is in this deeper section. And what we're really looking for is we're looking for this Synrift section. We're trying to image in that deep section in order to identify the Synrift sequence. And this legacy data doesn't really make it easy for us. You can see all this reflectors which seems to be maybe coming out of plane, but they might be real. We don't really know at this point. So we're going to focus on this area, and we're going to see what happens when we go from the legacy data to the reprocessed data. So watch what happens in that space when I go from this data to the reprocessed data. And I hope you can see that not only the shallow section is really cleaned up, we now have the continuity, we have that amplitude contrast that we need in order to differentiate what we think are reservoirs versus what we think are shales and where we think we might have our source rocks. But also, this section cleaned up completely. I've got here marked what we didn't know whether they were real reflections, and now you can see that this has got depositional geometry. It really looks like syndrift. It's got that wedge shape. And this syndrift section has appeared and has become a lot more clear. And if I now put some interpretation on here, you can see that we can interpret the basement. We've got the syndrift section, and we've also got some possible syndrift half grabens over here, where we could have this lacustrine source rock deposited, and we could have some of this source rock kitchens at this level. So it really is critical to have this reprocessed data in order to be able to carry out some of this analysis. And the other thing that came out that was very exciting with the reprocessing back in 2018 are these shallow amplitude anomalies, very, very clear. You could see them before in the legacy data, but they weren't as clear and they didn't stand out as much. But now with the reprocessed data, you can see them very, very clearly. And you can see that change in phase. You can see the high amplitude anomaly. You can see the soft kick below the hard kick. And some work had already been done on this. So there is a publication which everybody talks about. It's one of those classical publications that just becomes one of those papers that everyone refers to. And this is the Baristas et al. 2012 paper, where he did an analysis of various hydrocarbon leakage indicators. And then what you see here are the classification of those indicators and the interpretation of where that hydrocarbon could be coming from. And this is great work. So he identified, as you can see, two areas with significant features indicating that there is a working and active hydrocarbon system that is generating all these features. So what we did is with the reprocessed data, you can see the great enhancement in the imaging. We took this reprocessed data and we did this analysis as well. So we did an analysis of around 11,000 kilometers of 2D, trying to see if with the enhanced imaging we could see maybe additional features to what Baristas had already seen. So we set out to looking for bright spots, flat spots, and phase reversals. So I'm going to show you some examples, some very nice examples of what we actually found. So I'm going to, you can see the seabed is a white kick. So, sorry, it's a white reflector. So black is a soft kick. And here we have a very interesting soft kick, which is underlain by this. So the top is a soft kick and the bottom is a hard kick. And I'm going to zoom in on that so that you can actually see this continuous reflector above, whereas this reflector actually changes phase. So you get this phase reversal from soft to hard. You've got this soft top, this hard kick at the base, so a very, very clear DHI, a very clear direct hydrocarbon indicator. And you've also got this slowing down and this frequency, the increase or the decrease in frequency in this bottom section. And then this suppressed signal under the anomaly. You can see that a sort of gas cloud. So that's the kind of feature that we set out to look for. We also found some very clear type 3 anomalies. So here you have in the near stack very bright amplitude anomalies with very clear, again, DHI indicators, bright amplitude anomalies that are changing phase, soft kick over hard kick, soft kick over hard kick, and now this is a near stack, so I'm going to go to the far stack so you can see what actually happens to the amplitudes. The amplitudes are enhanced, so it's a type 3 AVO anomaly, so we have brightening in the far angle stack. Not only that, but can you see how this pushing down, this push down effect is actually enhanced in the far angle stack, and that is again a very good hydrocarbon indicator. So we used all these hydrocarbon indicators, and what we did in the end, or what was done in the end, was mapping of all these leakage, hydrocarbon leakage indicators, shall we say, and we overlaid it over the Baristas map. So this is area 1 and area 2. You can see in area 2 we had pretty good consistency. It was very close to what they had found, but here in area 1, and particularly in this area to the north, we found a lot more hydrocarbon indicators. So we actually extended the area of these hydrocarbon indicators to the north. Now, we thought that could have been maybe due to having better seismic quality. That's one possibility. But maybe also there is something else that's going on. And this is what we try to understand. What is going on geologically that we might have this higher density of hydrocarbon indicators here in the north? So this is from the Baristas paper again. I use it quite a lot because it's a very good paper. It's trying to understand, so this is from area 1. This is the geoseismic section over area 1 and over area 2. So it's a northwest, southeast oriented section with an interpretation of all the faulting and an interpretation of the migration pathways and the different hydrocarbon types that are being produced. So as I said, there are two major source rocks, the Cretaceous source rock, and you've got also your Cynriff source rock, the Tobifera Formation, middle to upper Jurassic. So here, it really, according to this paper, they see that the main hydrocarbon source would be the Cretaceous source rock. And what they then say is they invoke long-distance migration from this Cretaceous source rock kitchen into area 1, and they consider that to be the main hydrocarbon source for the leakage observed in area 1. So they also see this as being a potential or inferred source rock, but a minor contribution with a lot of question marks. So really they're thinking that there is this long-distance lateral migration from this area to Cretaceous source rock. In order for that to happen, you need for this to be a very good seal. So you can see how they saw that the faulting actually changes from the southeast to the northwest. So you have an area with no faulting. That is essential in order for this to happen. For this long-distance migration to happen, you have to have very good seal here. Well, let's see what our reprocessed data set says about this area. This is an incoherence view of the reprocessed data. And if you focus your attention on this shallow section, you'll see that really there is faulting throughout the whole of this section from the southeast to the northwest, and we don't really see any evidence for no faulting here and a seal here. So the question is, where is the hydrocarbon in leakage area 1 coming from if it's not coming from the Cretaceous, main Cretaceous source rock in the southeast? That is the big question here. So one of the ways to address it is to do a very detailed facies mapping. So using a modified Ramsayer method, Krista undertook this very good and very powerful facies mapping, where she identified for both the Cynriff section sequence and the Cretaceous sequence, she undertook to identifying all these different facies types. And the different facies types are indicating, again, well, different environments and different facies. These were then mapped, and they actually provide a lot of insight into where the source rock might be coming from. So let's first look at the Oxfordian to Tithonian paleogeography map that was derived from that facies analysis. And here you can see that in orange is that high amplitude chaotic and discontinuous facies in the north. That's interpreted as volcanics and volcaniclastic conglomerates. And then this deep green, or this deep graben depot centers, were interpreted to contain this interbedded tufaceous sands and clay stones in an anoxic environment. And that again came from the facies analysis. And now look at the distribution. Remember I said there was a high density of these VHIs, or these hydrocarbon leakage indicators, in the northern part here. Well, they are very strongly associated with these half grabens. And now if we move over to the Hutterian, Barremian paleogeography, you will see that again using the facies, this was interpreted to be active deposition in the inner to middle neritic marine environment in the north, and this transitions to utter neritic to upper bathyal hemipelagic and pelagic deposition in the south. And here in the south, we see this again high density of hydrocarbon leakage indicators. So a much simpler model, which we feel that all the evidence from the reprocessed seismic data supports, is that we have in Area 2 the charges from the Cretaceous, and in Area 1 we believe it's Jurassic origin. So this makes this Jurassic source rock a very viable source rock, very important source rock that we need to identify in our seismic data. So now I'm going to show you the reprocessing from our second phase of reprocessing, 2020. Just hot from the oven. This has just come out. And if I may point your attention to these areas that all these blocks were awarded and there were no offers placed on these two areas that are highlighted here. And I'm going to show you data from those two areas. So I think it's understandable why nobody placed an offer, why companies didn't place an offer on this particular area, because if I had this kind of data, I would say, I'm not going there. Very thin sediment cover. I don't see any syn rifts. I don't see anything here. It's full of multiples. It's very discontinuous, very difficult to interpret. So this is before reprocessing, and now watch what happens when we reprocess this data. It's like night and day. Night and day. I mean, that's the only way I can describe it, because suddenly we are now seeing these reflectors, even in the shallow section, the improvement is very impressive. I mean, you now have this continuity, you have the amplitude content, which helps you distinguish, hopefully, between your reservoirs and your shale or shale-dominated sequences, but really, really importantly, and this changes our view on the petroleum system in that area, is the syn rift section is revealed. So suddenly we have this opportunity for the syn rift source rock to be present and be generating hydrocarbons with a thick enough sediment cover. So here's another example, before and after. And again, we get that same response where we just really improve the imaging in the shallow section, but more than anything, it's revealing this syn rift section where we have all these syn rift tilted fault blocks where we infer source rock, but also suddenly some structures appearing here, and this looking like a very nice shale-rich, shale-dominated sequence. That's probably our Spring Hill Formation. It just opens up the possibilities for the petroleum system in this area. I mean, I could go on and on, but this is just one more example before and after. You can now see the syn rift. You can see a structure. Again, we can infer that there might be some hydrocarbon migrating into this horst. And then, again, in this area to the south where we have the fold and thrust belt, we have this beautiful amplitude anomalies, very nice, very clear hydrocarbon indicators with this gas push-down effect or hydrocarbon push-down effect, very clear, soft kick, hard kick at the exit of the reservoirs, thick reservoirs because we have flat spots, so at least 20 to 30 meters, thick reservoirs with very clear hydrocarbon indicators. So what we did here is we undertook, I wasn't able to cover this, but what we have is we have this web-based platform where we host all our data, and we have an API attached to it where we can run machine learning with machine learning capabilities. So what we did is we trained the machine. This is supervised deep learning neural network using Google TensorFlow, and actually semantic segmentation, which means that we are identifying geobodies and not just bounding boxes. So what we did is we undertook to identify the gas, what we think are shallow gas anomalies, and not shallow gas anomalies. And this is just really to show you the example. So red is gas and purple isn't. Red is gas, purple isn't. Red is gas, purple isn't. And then what we do is we have this, we used Mexico, PNG, and Argentina data sets to train a machine. And this is an example of a stack. I'm going to overlay the results, the probability of actually having a shallow gas anomaly on this stack. It's like overlaying your velocities on a final stack. And these are the results. So you can see that the machine has done a really, really good job at identifying the shallow gas anomalies. So what is the point of doing this? Well, we start off with Baristas et al. Great work that he did, and he identified all these hydrocarbon leakage features and classified them. Then we have Krista Davis presenting at the APG in 2019 and expanding and extending the area with hydrocarbon leakage and actually to the Sindrift half grabens and explaining some of these high density of hydrocarbon leakages. That took her a few months. I don't know how long it took Baristas. This took the Krista a few months. Yes?
We have 4 minutes left.
Okay, I'm about a minute away from finishing.
Okay.
And it took the machine 15 minutes to run through the whole data set and come up with the distribution of stacked shallow gas anomalies. And you can see again the relationship is very clear with the Sindrift half grabens. So together with this understanding and the better imaging that has shown us that in some of these areas that there were not even any offers made by any companies, we have this Sindrift section. It opens up and just changes our view on the prospectivity in the Malvinas Basin. And we have shown this to the Secretary of Energy in Argentina, and they're thinking of potentially adding these blocks in the round because the evidence is so compelling. So we're very happy with the results here. Thank you.
Sorry, I was mute. Thank you, Karyna. Very nice presentation and very nice seismic images. Actually, the question we got and is people are mostly interested in seeing if there are more examples of the pre-stack reprocessing at the searcher website.
Not so much at the searcher website, but they can definitely contact me, contact us, and we will be very happy to share more examples with them. Yes, because we do have a lot of very good examples.
I do have one question about the whole system here at the Malvinas, because we looked at this in the new ventures in the previous round. And have you seen any relationship between the oily phase or the gas phase, any distribution in the basin, and you can point using the seismic, or my question is, will you say that we have more potential for gas accumulations in the deeper part of the basin, or than in the distal place?
Yeah, I think that's a really good question, very fair question. I think, look, you have deep burial here because of your fall and transfer of your foreland basin and the very fast filling of your foreland basin. And it looks like it's your Cretaceous source rock that is providing these hydrocarbon leakage features. Where I showed you the very clear DHIs, which are probably more associated with gas, was in this area around here. So that's maybe indicating that we are generating gas, probably from the Cretaceous source rock. But when we move up here, and we move into this area where we have the Sindrift half grabens, the DHIs are not so clear, and yet the hydrocarbon leakage is very clear. So we have this clear shallow gas amplitude anomalies, but in the deeper sections, all the reservoirs that would have tapped or would have had access to this source rock are not showing us this very bright amplitude anomaly, so probably more indicative of potentially having some oil accumulation.
Okay, that's very interesting. Thank you, Karyna. Thank you very much for the presentation. Very nice.
Thank you. Thank you very much. And thank you again for having me. Enjoyed it. Thank you.
Thank you. Bye.
Thank you.
Hello, Gabor. Can you hear me?
Yeah, I can hear you.
Okay. So now I have the pleasure to introduce Mr. Gabor Tari. He's the Group Chief Geologist for the OMB Petroleum Group, and is responsible for all the geological aspects of the global exploration portfolio across the business for OMB. And he has worked for different companies. He worked for Amoco in Houston, and he's a geologist and geophysics from the Rice University. And in 2007, he moved to Vienna and has been working for OMV since that year. And Gabor is also quite interested in education, and he's a adjunct professor for Rice University and the Vienna University. And he's a quite active member at the American Association of Petroleum Geologists and other associations. So, Gabor, thanks for being with us, and please go ahead with your presentation. Thank you. Well, I think your microphone is mute. We cannot hear you.
Can you hear me now?
Yes.
Okay. Then let me just share the PowerPoint. Here we go. So I thought this might be an interesting topic for a 25 minutes talk. Inversion tectonics. It's important for our business overall. To dive into it straight, this is just a little visual reminder of what it is. I'm going to talk about positive structural inversion. And the definition is kind of wordy, but it's very simple. You had at one point an extensional system, and then the very same fault set responsible for the extensional deformation will be reused later on in a compressional or contractional sense. And this is the cartoon by Albert Bali from 1984, which tells you the story quite nicely. And of course, this concept, which got on the road about 30 years ago, became quite important for the exploration community because we do come across traps and petroleum systems which are the product of inversion one way or the other. And some of the petroleum system elements like reservoir and then source charge and of course trap and sealing to a large extent will be all the product of the inversional process. I'm not going to get into the details, but intuitively it's clear, for example, that the extensional phase could influence the deposition of reservoirs closer to the master fault. And then you could have a source rock like this light green stuff at the bottom, and that's going to be affected by the inversional process. Now, what we did, and this is kind of new, is that we tried to have a feel about the importance of inversion in exploration and production business worldwide. So we were digging into this worldwide database by HS Market, and we were looking for discoveries and actual producing fields, which were described as some kind of product of reverse faulting or thrust faulting. And here you can see that, if you see my cursor, the trap form type category. Now, I just show a little piece of this humongously large data set. We had 2,000 hits in this category, excluding onshore US and Canada. And when we were starting to analyze this data set, and we were looking for inversion as the trap forming mechanism in particular, we were kind of surprised that out of this big 2,000 cases population, we just found 60 cases where inversion was mentioned. So the takeaway from this slide is that inversion is really a kind of a underappreciated beast in our business when it comes to producing fields. Now, let me show you some seismic examples from here and there, just to kind of remind your visual sense how inversion looks like. Let me take you to onshore Egypt. This is one of those classical situations, onshore Western Desert. This looks pretty good. You can see this big extensional Jurassic half graben below, bounded by the Rosetta Fault. And you can see this kind of culmination on top. And that's a clear sign of inversion. Still sticking to onshore Egypt, another famous example, Mubarak anticline. And then here you can see a very clear asymmetry, and you can see the fact that you do have a thickening early on within the structure, and then that's being replaced on top by thinning. So extension was preceded by conversion at a later point. And the whole thing is kind of asymmetric. It's almost given the fact that we started out with an extensional half-graben. Now, if we zoom out and look at the Mubarak inversion, the seismic example I just showed you in a regional context, this is a regional section across the Western Desert onshore Egypt. You appreciate the fact that not all of the pre-existing extensional half-grabens will or would reactivate in a positive inversion sense. Many of these features, if you look at it, they just don't react. So it has something to do with the fact how the master fault is situated in relation to the stress field in a map view sense. What are the exact geometries and the timing and such. But something to keep in mind that it's not always a given that every single pre-existing extensional structure will be positively inverted in your region. Let me take you to another place in North Africa, onshore Morocco, a little bit closer to Portugal or Lisbon, if you will. And this is a case for what I call the mild or minor inversion. You do have this big underlying Triassic half-grabens, and you do see this beautiful coincidence of very low amplitude, gentle anticlines on top, involving the Jurassic, Cretaceous, and the Cenozoic. And this is really a nice case for just a touch of inversion during the alpine deformation. Let me show you kind of an extreme case, the classic area, Indonesia, if you will. Here you can see a case where you do have a little bit of pre-existing extensional element, as you can see from the thickening-thinning relationships, especially in the core of the anticline. But on the master fault, you don't see any of the normal offset preserved. This is all reverse offset. Very interesting. Let's come back to the northeastern Africa, if you will, Egypt, the Levant, Israel, and Syria. And Bill Bosworth showed very nicely that there are two elements here. You have regional scale inversion, which is shown in this medium brown area. This is the Syrian arc inversional belt, if you will. And I'm going to show you some examples from this very region. And you can see the pre-existing reef fabric in this medium green color. And the inversion is really superimposed on this pre-existing reef fabric only in this part. I'm going to show you one offshore example and then one onshore example. The offshore example will be from Israel, the famous Tamar, Leviathan, and Aphrodite examples. I took these samples, took these maps from published literature, and I'll show you afterwards one onshore example. And I will ask the question, are these really good examples of inversion, structural inversion, the way we understand them? So the first example is from offshore Israel. It's a very, very long line, almost 200 kilometers long. You see on top the Messinian salt. But what's important for our story is these big bumps down below, and especially this one where the Tamar discovery was drilled by Noble more than a decade ago. And this turned out to be a fairly big discovery, as you know, 7, 8, 9 TCF in size. And then the question as an explorer that this is obviously an anticline of some sort, but could we call this a case for inversion, positive inversion? Does this bump have anything to do with this underlying synreef fabric, which is obviously not drilled at this point of time? So if we zoom in, the important thing is that you don't see any kind of fault control on the sides of this anticline. You do see a little bit of asymmetry, which is good, and then the field, the gas field was found here. If I show you some published images across the Tamar field, this was the discovery well. And again, you see a good-looking anticline, which mapped out as an anticline in a map view, but you don't see faults, which would be bounding the whole thing on either side. These cross-cutting piano key faults as a different story. But here it is. So this is a beautiful anticline, and the question is, could we make a case for this bump and many other, like the Leviathan anticline, is really the result of structural inversion, because we really don't have a physical fault connection all the way up from this Sindrif grabens all the way along the flank to this anticlinal features. The answer is yes, this is indeed a case for inversion, but if this seismic is not convincing, which it is not on its own, what one has to do is to look at the whole thing in a regional context. Regional geology is always very, very important for exploration, so you have to look around. And in the case of offshore Israel, you have to move a little bit inboard, and you find some other analog structures which are a little bit better understood, and they were drilled deeper, and then the seismic below them is a little bit more convincing. And these structures are really the product of a positive structural inversion, as you could see, for example, the relationships below the Yam West. Well, basically, here you had some kind of late Paleozoic Triassic extension of fabric, and after a long silence, the entire Jurassic and the early Cretaceous, by the time you get to the late Cretaceous and then the Cenozoic, then you do have a case for contractual deformation. If you look at this area, it's quite interesting that in the very same area, you do have a lot of inverted features. This is the Sinai in Egypt going to Israel, and you have many of these features, which are very well described in the past, but they fall into two categories. The inboard ones in black are the early Syrian arc features, which are a little bit older. And then if you go to the deep water, you have these younger features like Tamar, as I showed you earlier, which are basically operational during the latest Miocene or even into the Pliocene, around the Messinian, if you will. So it's a very interesting relationship looking at the offshore Levant. Now, if I take you to this other example, onshore Syria, the question for the Palmyrids is that are we looking at inversion, positive inversion here or not? And if you recall the definition from slide 1, we would have to have some basement involvement, sensu stricto, to call these features inverted structures. And we don't have that. We have detachment here along this Curacina upper Triassic salt. So sensu stricto, these are not inverted features, even though they are located in the same contractual compressional Syrian arc deformational belt. So that's something to keep in mind. Now, let me come back to the strictly exploration kind of implications of how we should look at the inversion. And there's this story from Egypt again, what I call the Goldilocks concept, how much inversion you want to have in order to have the maximum impact for your exploration expectations. And of course, intuitively should be obvious that you have to have some. This is the mild case under A. And then if you start to increase the amount of contraction on your pre-existing structural fabric, then you could have more and more traps, but you could reach a point where your traps will be busted up and you will have a lot of problems with breaching. Your seal is not going to work, and then you might end up drilling polio oil accumulations because of the too much inversion, if you will. So this is important in the sense that we would try to have a handle on how much inversion is really ideal for an explorer. And in order to get there, one would have to kind of quantify the degree or amount of inversion in any one case. And there are two subdivisions or two methods out there which would try to quantify the amount of inversion. I'm not going to describe neither one of them because it's a little bit complicated. But the point I'm going to make here is that you would have to have a lot of information geometric information, subsurface information about your structure in order to do these calculations shown on this slide. It's just not very practical because sometimes you have seismic, which is vintage, and it's just 2D. Onshore, you won't see much below the structure. So you cannot really go through this calculation. You cannot really put numbers on the degree of inversion. So one thing I suggest here is a more practical approach. Perhaps it's not so quantitative like the ones shown before, but if you just go with this basic geometric values, like the overall uplift, surface uplift above the regional, due to the inversion, that would be A, and then you kind of relate that to the overall map view width of the pre-existing extensional feature, then that ratio is actually, in our view, a pretty good description of how much inversion you are dealing with. You don't have to see the deep part of the half-graben at all. You don't have to have a good handle on the offset along the muster fault on the left. So this is just a side note to get into it. And another observation or kind of a challenge I like to table here is that I think, generally speaking, we are a little bit biased as far as how we think about inverted features. If you look at all the physical experiments, and I'm going to talk about a friend of mine's work, McClay's work, what you do see is an emphasis on a very thick pre-extensional or extensional feature and a relatively thin or skinny post-extensional or semi-inversional sedimentary layer. This is what's kind of burning into our visual expectations. But the examples I show you, especially from the Levant, should tell you that that's not always the case. So what I'm saying here in this diagram is that on the left-hand side, this is the classical kind of image we all grew up with, or at least I did for the last 30 years, is that you have to have the emphasis on the Sindrift system, the half-graben, it should be very thick. And then typically you have a little bit of post-drift and you go into inversion. And your fields are, of course, sitting on top of the inverted feature, and then all the kitchen is sitting underneath. And some of your reservoirs are related to the Sindrift sequence. But the examples, I showed you the example of Tamar in particular. They are coming out from a different geologic setting where the proportions are different. So the Sindrift sequence is, I drew it the exact same, like on the left-hand side, but I like to emphasize that you could have, especially on the passive margin, distal passive margin, you could have a lot of post-drift sequence, which in thickness-wise is more, could be much more than the underlying Sindrift sequence. And if you invert something like that relatively late, then you end up having a buccal fault very, very high up over the extensional feature, and then your fields will be sitting in this post-drift sequence, and then the source rock or the generating kitchen will be not coming from the Sindrift source rock sequence at all, but they have to come out from this regional post-drift sequence. So it's a very different world. And I think this view is not fully appreciated by all of us. And if you look at, again, the physical experiments, you don't find physical experiments which would try to reconstruct or try to come up with geometries like this. Everything is revolving pretty much around this. There's a reason for that, but just to leave you with a conclusion in this sense, this case A or mode 1 is really true for failed drifts, proximal passive margins. You can think about the North Sea, Northwestern Europe, if you will. And the case for this right-hand side, mode 2, kind of inversion is really places like the Levant or the Black Sea. These are really Becker basins or the Pannonian Basin or distal passive margins. So if I want to sum up what I showed you briefly is that we went for this journey for the last 30 years, and what we do see is that the inversion as such, the definition is being a little bit abandoned by the petroleum industry and the academia. And I think clearly, especially in the production end, inverted structures are being neglected and then being ignored to a large degree. And some other conclusion I read out here is really, truly, what we cannot expect is that we always understand the deeper part of extension, inversion of features. We have to kind of guess the inversion, mostly from the regional geologic context. That's many times the best way to argue that we are dealing with inverted features. And I mentioned what would be the ideal trap formation, and in order to get there, we have to look at worldwide data sets. We are just not quite there. But this semi-quantitative classification I showed you briefly is one way to try to categorize inverted oil fields or inverted structures rather in those oil fields. And this will be an interesting exercise. And again, the last conclusion I showed you is that one could or one should think about really about two end members of inverted structures. And that all depends on the ratio of the scenery versus the positive sedimenting cover. And if you accept that a proposition, then you start to realize that the associated petroleum systems and the prospectivity could be very, very different for these features. And with this, I'm going to finish this presentation. Thank you for your attention.
Thank you, Gabor. We don't have a question from the audience, but I do have one question, and is you mentioned the possibility of sometimes drilling paleo accumulations or paleo or structures that were uplifted and had an oil accumulation in the past. Could you mention some examples, or did you see some of those in your exploration in Africa?
Very good question. Very good question. And for example, if you look at the UK, like the Jurassic coast down in the south, they have absolutely classic, beautiful inverted features, and they have a lot of oil seeps too. And it seems like because of regional uplift and kind of a little bit runaway inversion, regionally speaking, their structures, which probably had some hydrocarbon fields, they were all breached. And then if you walk along that beautiful coast, you see a lot of evidence for on the surface for oil seeps. And those correspond to Apollo accumulations. Of course, there is a very nice example which escaped the fate, the Witch Farm, which is a very big field. But that's just the only one field in that whole region out of many, many breached inverted features. So that could be one example probably everybody can relate to.
Okay, Gabor, thank you very much for presentation and your answer. Thank you.
Thank you very much for listening.